Okay, in this lecture, we learn about convolution decoding. And for convolution decoding, we review the maximum likelihood decoding procedure. Because in convolution decoding, we use maximum likelihood decoding. In maximum likelihood decoding, we compare the two conditional probability if the channel is binary. And whichever the probability is higher, we decide the decision accordingly. But in case of convolution coder, we have a sequence of code words. This sequence of code words contain different branch words. So we have for M message bits, we have the M code words. And we maximize the conditional probability of these code words. This is like this condition probabilities are like Markov process in which we based on the previous code words or the previous bits as well. And we maximize the conditional probability of the overall sequence. So, for example, if we find a person Neo, so what will be the maximum likelihood sequence for finding this person is that the probability of P1 is higher than the probability of this person. So P1 is the probability that the person is more likely to the real person, and the highest probability will goes for the real person, which is P7. So in convolution coding, we have the 2L number of paths in the sequence. For example, if we consider that we start from T1 to T5 time, so we have 32 possible paths emerging from this first T1 instant. So it is, in fact, is difficult to estimate that which is the appropriate path, because there is only one path which is correct among this 32 paths. So in fact, what we are calculating the probability, and we consider that the channel is Gaussian and affecting each symbol independently. So we can write the probability to maximize for all the sequence is the product of conditional probability in the sequence. And in this sequence, if we split this code word into the branch words, because if there is branches, if there are five different branches in this sequence of the code word, because UIM represents five branches and each branch representing 2 bits. So the branch word is of 2 bits, which corresponds to one message bit. So I is 1 and J is 2 for each branch word. So we will find the product of all the probabilities of n bits of the code word into the message bits. In general scenario, the message bit is 1 and the coded bit is 2. So by taking the log of this function, by taking the log of this function, we can transpose the product into the summation part, which is more easier. And this is called log likelihood function. And in this, we will replace all the function with the log of this conditional probability function. So to choose the possible path or the real path, which is in fact the transmitted corrected version of the signal, we need to use the brute force. And we need exhaustive comparison of 2L accumulated log likelihood matrix. So in this case, we need to reject the path by a brute force and to choose the other path. So the decoding in this stage is complex because you need to keep the memory of the previous path as long as you completely decode the sequence. So instead of the memory and the complexity, the decoding with the tree-like structure is very complex. So we need the maximum likelihood decoding for a trellis structure. In trellis structure, we have uh, the T1 time when we have two paths emerges at this time instant, and at time T2 we have four paths emerges from this sequence, and from T3 onwards there are 8 paths emerges from this sequence. So if you compare time T4, again you have 8 paths, and at time T5 again you have 8 paths. So the every instant, uh, every state converges 2 paths. So there is the possibility of one correct path with minimum with maximum likelihood criteria, and we reject one path. So, so the every stage we reject four paths, and we keep proceeding from 4 to 8, and then rejecting 4, and then from 4 to 8. And in this way, we reduce the memory and complexity of the coder. And here we are not using the brute force. So in trellis type decoding, which is called Viterbi decoding, uh, also using the maximum likelihood criteria, but it needs less memory and less complexity, because the earlier rejection of the paths in the sequence. So it is just like the best path will survive, and this path which is not suitable will not survive, will be eliminated, right? So the number of surviving paths can be calculated by the function 2k minus 1, where k is the constraint length, and k is the constraint length, and if the constraint length is 3, so the maximum surviving path is 4. So in our case, we have the constraint length of 3 and the code rate of 1 by 2. So we have this surviving path is equal to 4. So now we use the hard versus soft decision. Hard decision is that you ask a single question and you have to answer yes or no. So it is a hard decision. Sometimes you cannot answer in yes or no. You need more explanation to answer. And similarly, the way you ask a question is you need to ask many questions instead of a single question. For example, you want to know the age of a person, and you ask that your age is more than 40. So he can answer that yes or no. So in that way, you are not sure about his age. So you ask several questions. So after asking, after knowing the age is more than 40, so you need to determine that what is the exact age of that person. For these, you need to ask several questions. It means that you want to set the levels, and in that levels, you can predict what is right and what is not right. So in hard versus soft decisions is just like we have a binary channel, and we are using ML decoding, and in this we have 0 and 1. So if we decide directly between 0 and 1, so that is in fact is the hard decoding criteria, but the soft decoding will quantize the decision boundaries. So it will quantize the decision boundaries up to 8 levels, and these 8 levels will determine the confidence of your decision. So for example, if I say that I have the answer 000, so I can have a high confidence about the transmitted bit is 0. And if we have transmitted 111, I have a very high confidence that the transmitted bit is 1. So this quantized sequence will in fact will help us to determine the decision with the confidence. So this soft decision decoding will improve the performance of the decoder by 2 dB. And if we increase the quantization interval up to infinite number of levels, so there would be a 2.2 dB improvement. So it means that the 8 quantization and interval are appropriate for the decision of this binary 0 and 1. So in binary symmetric channel, we have the probability of erroneous decision is P and the probability of correct decision is 1 minus P. So in binary symmetric channel, if we have the code word transmitted with Hamming distance dm and the length of the code word is L, so we have the number of dissimilar bits is dm and the number of similar bits is L minus dm. So the conditional probability of the code word sequence is into the probability of the wrong decision times the number of differing bits among the sequence. So this is in fact is the received sequence and the branch word sequence. So this is the comparison between two. So this is the erroneous decision and this is the probability of correct decision. So the probability 1 minus probability into L minus dm is the corrected probability. By taking the log, we can translate it into the form of a sum. So we have minus dm log 1 minus p over p plus L log 1 minus p because we separate the dm terms among this sequence and we separate the L terms in the sequence and we will got this probability. So if the wrong probability is less than 0.5, then, which is obviously the case, so we can write this sequence as minus a times dm plus b. So here it is in fact is a the a and b are the constants. So we can calculate the uh, error probability, or we can calculate the uh, conditional probability in terms of Hamming distance. So we can translate it in the form of Hamming distance. So in fact, if you check the log likelihood function over the Gaussian channel, so it is just like the correlation among the sequence. So we find the correlation between the received sequence and the transmitted sequence, and we determine it in the form of Euclidean distance. Then we perform the soft decision decoding over that decision. So if we just see here, uh, if we just see here that the log likelihood function of uh, uh, the log likelihood function is of this conditional probability will be the summation of this two sequence product. So, so we consider it as a correlation, or the correlation is in fact is of this weight is just like this, and the every moment the correlation amount of correlation is increasing, then maximum, and then decreasing. And then we, with the law likelihood, or with the soft decision decoding, we can find the maximum possible transmitted sequence of this word. In Viterbi decoding, we also use the maximum likelihood decoding, and as I said earlier, that we are choosing the best surviving paths in the sequence instead of focusing on all the paths. So in this way, we reduce the complexity of the decoder and also reduce the memory required by the decoder. So, for example, we have L is equal to 3-bit message from the trellis, and we have a 3-bit message, and the constraint length is 3. So the number of branches, or the number of branch words, are L plus K minus 1. So that is, if K is 3 and L is 3, that is 5. And it goes from time T1 to time T6, right? So every time we determine the distance, we determine the state, the states, we determine the path of converge at each state, and we find the Hamming distance of this. So, so there are 2k minus 1 paths which will be survived to these states, and these states are 4 and these paths are 4, and we calculate the distance for these paths at these time Ti. For example, initially we have computed 0 for 0, 0 state, and that is the time T1. and we keep moving onward by calculating the path distance. For example, uh, we have we have 0 0 0 0 0 0 state, and we move to 0 0 state, then we get the output 0 0. We get the output 0 0. And if the received sequence is 1 1, if the received sequence is z is equal to 1 1, so this is in fact is the z uh, 1 1, and from this 1 1 we get 0 0, and two bits are differ. And when we move 0 0 to 1 0 state, we will get 1 in the output, and we will get at the output is equal to 1 0. So this 1 0 is we get the output is equal to 1 1. So this 1 1 is similar to this transmitted received bit sequence, and we have the 0 differing bits. So the every time we calculate the differing bits of the sequence. So here uh, we cannot terminate any path, because we keep proceeding these two paths, and we calculate the paths emerges from T2 time, and calculate the corresponding Hamming distance from the received branch for Z uh, 1 received 2 1, received 2 1, because it's JI. And we calculate the sum of the Hamming distance from all these paths. So this is the path distance, and we have the path distance. So here we will not compare, because we are comparing the likelihood of the sequence, because we keep these four paths to emerge again. So from these four paths, we have the 8 paths, and from these 8 paths, we choose, here we have T3 time, we have the 8 paths emerging from it. So every state emerges the 8 path, and from now onward, we will reject the 4 paths based on the Hamming distance. So every path, we compare the 2 paths. So one with the best distance, with the minimum distance, and one with the maximum distance. So we will calculate the Hamming distance of that path. For example, at this time, at this path uh, emerges at 0 0 state, and this path is also emerges to 0 0 state. So the distance is 4 and the distance is 3. So we will choose this path to survive, and we will keep the memory of this path. So the same way we will calculate the Hamming distance of all other paths and choose the 4 paths only. From now onwards, we have the we have the 8 paths emerges at T4 time, and we will again choose the best path. Now T5 time, we know that we have to terminate at the branch L plus K minus 1. So we have to terminate it to 5. So we have terminated to 5. So it means that at this time, we have choose the path. Finally, we have to make decision. What decision we will make? The decision we will choose all the paths which originates from 0, 0 state and terminates at 0, 0 state. We will not, we will, in convolution decoding, we will terminate the path where we will, where it joins the 0, 0 state again. So there are 2 paths which originates from 0, 0 state to 0, 0 state, and one with the path metric 1 and other with the path metric 4. So we will choose the path with the 1 path metric. So we will see it on the diagram that here we have from time T3, we have the 8 paths and we removes the 4 paths. And similarly, we have 8 paths and we remove the 4 paths. And then we finally choose the best path for this decoding. So here I'll show you the implementation of this decoder on the hardware. The hardware implementation is shown. So here you can see that we divide the implementation into 2 cells, cell 1 and cell 2. So the 2 parts are emerges at Ti plus 1 time, and we have the 2 parts emerges at B state. So the 2 parts emerges at A state and 2 part converges at B dash state. Similarly, 2 path merges at C dash state and D dash states. So we will keep the Hamming distance of the previous path, which is delta A, and we consider the Hamming distance of this branch into it, and we calculate it. So it is in fact, we will just add the path and then we compare, we add delta A plus delta A dash, and we add delta C plus delta C A dash, and we compare these 2 paths. And we reject one with the minimum Hamming distance. And similarly, on the cell 2, we do the same process. So we see the hardware implementation of cell 1. So here we have the delta A and we have delta C for the cell 1. And we have delta AA dash and delta CA dash we add, and similarly we have delta AAB dash and delta ACB dash. And from this, what we are doing, we compare the two distances and then we select the Hamming distance of the current path, of the best path, and the message bit of the uh, message bit of the two paths selected. Uh, we select the message decoded from these two paths. And so this is in fact is the path memory and this is the path Hamming distance. And similarly, we calculate for delta B dash and MB dash. So this is in fact is the decoder implementation of the Viterbi decoder. So we need to compare the performance and gain of convolution codes, and this can be determined in that way that all the paths originates from AA and all the paths terminate at A state, which is mentioned here E here. So you can see that either we move this way, either we move this way, either we move this way. So we have the different path distance. So this is in fact is the shortest path with the Hamming distance d5. So that minimum distance is called the free distance of the code word. So this df5 of path uh, of path uh, 00 to 10 and 10 to 01 and 01 to 00 is the shortest path, and the value, if you multiply the distance d2 with d2, that is d5, and that is the minimum free distance, and that depends on the capability of the code to correct how many errors. So that is again like the convolution code has the linearity, and we have the property of d min replaced by df, and that is df minus 1 by 2. Now let's see that how can we write the transfer function of this uh, convolution coder. So for XA, how many paths emerges? There is no path converges to A state. So here in B, so there is D square XA is a path which is emerging, and the other path emerging to it from XC with 1. So here we get the XC. So the every state we have two paths emerges, and we have minimum two possibilities of calculating this path. So we write all the four equations, and from all these four equations, we calculate the value of xe over x a. So we calculate the value of xe over xa. So here we have xa, and here we have for xe. So the transfer function is in fact is d5 1 minus 2d. If you divide it, you will get the values that how many paths with how many distance we have in this. So this is the path with the minimum distance of 5 in the uh, in the convolution coder, in this convolution coder. So if we add the number of ones in the matrix, so we have the n factor added into it, and we have the transfer function reduced to d5n 1 minus 2dn. And from this, we calculate by putting the value of n is equal to 1, we calculate the upper bound for this. So the probability of upper bound is d5 1 minus 2d, and if we put the value of d is equal to p1 minus p under root, so we will have the value of this is given here. So the probability here will be reduced in this form. So the value of d is in fact is given here. So in fact, there are various parameters which improve the performance of convolution code, in which the code rate and the free distance are the two main factors which improve the coding gain. And also the error performance is improved by increasing the constraint length. So for any value of bit error rate, you can check that the performance is improved going towards left, and it is improving by increasing the constraint length of the code. So we have the different convolution coders with best performance, 1 by 2 code rate with 3 constraint length with 5 free distance, and with these generated polynomials. And similarly, we have the other two convolution codes. So commercially, we are using a constraint length of k is equal to 10. So there is a problem in the convolution coder that the error is propagated propagated if the generator polynomial have the same common factor. If the generator polynomial has the same common factor, like 1 plus x square is G1 polynomial and G2 polynomial is 1 plus x. So this generator polynomial is in fact has two factors, 1 plus x and 1 plus x. So what will happen if these two generator polynomial has the common factor? So the error, if there is one symbol error, it will be propagated for a consecutive uh, symbol errors, and that cannot be overcome. So that catastrophic error can be removed while designing the coder. So the connection vector or the generator polynomial will be decided carefully. So before Viterbi decoding, we use the sequential decoding based on tree structure. So I just give you the idea, though that is not useful and practically implementable. So in this, we choose the best path from the tree structure. And we can see this sequential decoding. In this sequential decoding, we can say that we have the received sequence 1, 1, and we compare it with 1, 1, and the distance is 0. So we will choose that the transmitted bit is 1 and we goes down, and we will choose this path. So, and in the next path, we have the decision that we move up or we move down. So here the decision is that the transmitted bit sequence is 0, 0. And in both cases, we have the minimum Hamming distance 1. So arbitrarily, we choose 1. So we choose 1 and we move up. And so the total distance will become 1, and then we take 0, 1. And 0, 1 with 1, 1 have a distance of 1, and the total distance of the path will be 2. So then we have 1, 0, and then we compare it with 0, 0. So there is one distance and we have the path of 3. So 3, we have to set a threshold that the number of disagreements, the number of dissimilar bits, if increased by 3 or it is equal to 3, so we reverse the case. So we should go backward and the minimum distance is 2 again. And then we compare it with 1, 1, 1, 0, and the distance is 3 again. And we choose goes back again, and we goes follows this path. And again, when the distance is equal to 3, distance is equal to 3, so we will reverse the path. So ultimately, by moving down, we gradually moving down, and we finally choose that all the upper block is not suitable for match, and we move back, and we will decide that the transmitted bit here is 0, where we have arbitrarily choose 1. And then again we move, and when the distance is approaches to 3, we will move back, and then it is again 3, and then we will move back, and this approaches to 1, and then 2, and then we finally decode this. So we will find the transmitted sequence, this according to the decoded bits from the decoder. So this sequential decoding is very complex and is less utilized. So next is the feedback decoding. In feedback decoding, we calculate the Hamming distance of the upper half metric and the lower half metric. So how we choose that, we split it at time t3. We split it at time t3 and t4. So T3 to T4, we have the 8 paths. So we have the first block. We have the first block started terminating at this point, T4 time, at this. And we calculate the path distance of every path. So the upper block, which has the 4, 3, 3, 1, and 6. So this branch, 1, uh, 1, 2, 3, 4, which emerges at T time, T3 time. So, and we have 1, 2, 3, and 4 for this lower block. So first we decide between the upper block and the lower block on the basis of the Hamming distance. So once we decide that we have to choose the upper block or lower block, in this case the path metric of lower block is uh, minimum. So we go downward. So we go downward one path. So we have the we next we choose the upper block of this T4 time, of the path emerges at T4 time, and the lower block of, so in that way we coded the second bit, and in that way we will move in the upper block and the lower block, and we will choose the decoded bit sequence. So this is the feedback decoding and all about convolution decoding. So for detail, you may consult the references. So for these references, you can further study about convolution decoding, and I will upload the assignment related to these uh, assignment, the convolution coding problems.